Hello, my name is Cristina González Gonzalo, and I am a last year PhD student at the AI Research Group, part of the Theory Lab. In this lecture, I will talk about the importance of AI ethics and explainable AI in medical imaging, and present our latest work in this topic. As you might have heard, deep learning has been shown to achieve close or even superior performance to that of experts in different medical imaging applications. For example, in ophthalmology, for the detection of diabetic retinopathy in color fundus images. You can see here a graph showing how a deep learning system, the black curve, outperforms multiple medical experts, the color dots. Also in dermatology, for the detection of different types of skin cancer, or for scoring of prostate cancer in histopathology images. However, several questions arise when it comes to the integration of these systems in real-world clinical settings. Can the system be used with different populations? Can I trust its decisions? Who is responsible of a wrong outcome? AI ethics cover these questions and aim to establish guidelines to mitigate associated risks. These guidelines include, in general, the FAST principles: fairness, accountability, safety, and transparency. First, fairness. It is important to acknowledge that the systems are designed by humans who are bound to the limitations of the context and biases, and this can translate into the systems. For instance, bias can happen in data collection and annotation. It is crucial to ensure that training and testing datasets are representative enough, including data from different populations and minorities, in order to avoid medical errors and discrimination in usability. It is also necessary to analyze bias during the design of algorithms, as well as bias related to their outcomes, in order to avoid discriminatory impact. During implementation, it is also important to ensure systems are deployed by users who are trained to apply them responsibly and without bias. The principle of accountability demands that the responsibility of AI decisions fall on the human developers and the users that apply the systems in the clinic. Answerability responds to who is accountable for an outcome, whereas auditability responds to how developers and users are to be held accountable. It is crucial to monitor accountability in all stages, from system development to the point the system is applied in clinical care and when it is finally retired. The principle of safety requires the system to be accurate, to operate within an expected error rate depending on the clinical setting, reliable to generate consistent outcomes, secure to ensure patient data privacy and confidentiality, and robust to ensure operability even with unexpected changes and perturbations. Lastly, transparency. Limited transparency can reduce trustworthiness of AI systems, as well as hinder the validation of clinical outcomes and the identification of errors and biases. That is why it is necessary to justify all the processes followed during the design and the use of the system, as well as understand the rationale behind its decisions or behavior. In this last aspect, we can include explainable AI, whose goal is to make AI decisions more transparent and trustable. We will focus on the importance of explainable AI in medical imaging. Among the main benefits of integrating deep learning systems in the clinic is that they provide diagnosis support. Deep learning systems can identify features in medical images that are invisible for human experts. They also reduce subjectivity in decision-making, and they reduce time and money resources. However, deep learning systems are seen as black boxes due to the lack of interpretability of their predictions. This is especially problematic in healthcare applications. Let me illustrate this with an example. Diabetic eye screening is a test to check for eye problems caused by diabetes, that is, diabetic retinopathy. In the UK, people with diabetes have their eyes checked once a year to find problems before their sight is affected. This is done in a point of care by an optician or a general practitioner who takes pictures of the back of the eye to check for any changes. If no changes are found, the patient is sent home and will come back in 1 year. Otherwise, the patient is referred directly to an ophthalmologist and will be there checked for possible treatment. If AI gets integrated in the workflow, the image is sent also to the system, which outputs a prediction, in this case, referable or non-referable. Even if the performance of the system might be at the level of experts, this yes-no diagnosis is far from the way the human expert diagnoses, generating a report about the decision and communicating with the patient. This hinders experts' trust in the system's decision, mainly due to concerns about the consequences and the accountability of a wrong diagnosis. This makes it harder to integrate systems in clinical settings, and the mentioned benefits are lost. So how can we open black box AI towards explainable AI? Most of the systems perform a classification task using a convolutional neural network or an ensemble of them, to provide a score for one class or several classes given one image as input. In the eye screening setting we described before, it would be a score to classify between referable or non-referable diabetic retinopathy, given a color fundus image as input. A common approach to generate an explanation of the system's decision is to provide visual evidence, identifying which regions in the input image are relevant for the system to make such decision. Several interpretability frameworks have been proposed for different medical classification tasks and imaging modalities. Most of them provide visual feedback of the system's decisions. One example is for the detection of skin cancer. In X-ray, for bone age assessment or detecting bone fractures. Or in ophthalmology, for the classification of disease features in optical coherence tomography and color fundus images. All these examples are based on visual attribution methods. They allow to highlight features in the input image that contribute to the output prediction. In medical imaging, regions discriminant for the diagnosis. In literature, different methods have been proposed, such as saliency, guided gap propagation, integrated gradients, GradCam, or guided GradCam. The systems are trained using only image-level labels that categorize the image as a whole. Visual attribution leads therefore to weakly supervised localization of abnormalities, which provides clinical explanation of the predictions without the need for costly lesion-level annotations. However, these frameworks have also several limitations. First, they localize only the most significant regions, and lesions that have less influence in the classification result are ignored, although they might be also relevant for disease understanding and scoring. Some frameworks do not consider that certain medical applications require to localize different lesion types, lesions of varying appearance and composition that can be simultaneously present. And most approaches do not evaluate quantitatively if they are actually including the regions considered by medical experts. The goal of our recent work is to improve deep learning interpretability and overcome these limitations. For this purpose, first, we need to train and validate the system to solve an image-level classification task, and then extract visual evidence of the predictions using any of the techniques mentioned before. In the AI research group, we work with retinal imaging, so we focused on two related tasks: automatic grading in color fundus images of diabetic retinopathy, or DR, and age-related macular degeneration, or AMD, which are two leading causes of blindness worldwide. For the training, validation, and testing of diabetic retinopathy grading, we used more than 88,000 color fundus images annotated at image level. For AMD, we used almost 134,000 images, also annotated at image level. The first picture shows a healthy retina, whereas the second and the third picture show referable cases for DR and AMD, respectively, with specific types of lesions. I will guide you through our proposed method, which is called iterative visual evidence augmentation. As mentioned, we first need a system that has been trained and validated to solve a classification task. In our case, we want to detect referable diabetic retinopathy. We have an input image that we process with the system and we obtain a prediction. If the image is considered as non-referable DR, the output will be a non-referable diagnosis. If it is referable, we then ask the system why it made such decision. We extract a visual evidence map of the referable prediction with a visual attribution method. This map highlights areas in the input image that are responsible for the decision. We then binarize that map and obtain a binary mask with the most relevant regions. We then apply selective inpainting to the input image over the areas included in the binary mask. The aim is to make the image healthier by erasing lesions that have been already highlighted using surrounding local healthy information. We send the modified image to the system and obtain a new prediction. If the output is non-referable, we stop the process. If it's still referable, we repeat the process. The prediction will go down as we iterate through the process until the image is considered as healthy by the system. When this happens, we combine all the visual evidence maps extracted in each iteration and generate an augmented visual evidence map, which will be the output together with the referable diagnosis. I would like to show you some examples of interpretable DR and AMD grading. We can see in the first column two images correctly classified as referable DR and referable AMD correspondingly by the system. In the middle column, we can see the initial visual evidence generated by the system, whereas in the third column we can see the augmented visual evidence generated after applying the iterative augmentation. We can observe that the augmented visual evidence maps contain more lesions, including those that are less discriminative but also important for diagnosis. They also include abnormalities of different types, shapes, and sizes. Another main goal of our work was to validate quantitatively the weakly supervised localization performance of the visual evidence maps and see if they are including the biomarkers considered by experts for diagnosis. This is possible by having a set of images annotated at lesion level. For DR, we use 89 images with expert lesion level annotations, with 4 different types of diabetic retinopathy lesions. In the case of AMD, we used 64 images where experts annotated 2 different types of lesions. Our validation did not only show that visual evidence maps contain the biomarkers considered by experts, but also that applying iterative augmentation to the visual evidence leads to a global increase in localization performance. In conclusion, we saw that AI ethics in medical imaging aim to consider fairness, accountability, safety, and transparency for the integration of systems in real clinical settings. It is often said that deep learning systems are a black box, but this is not true, since there are multiple approaches that allow us to open that black box and move towards explainable AI. In medical imaging, a popular approach is to extract visual evidence of the system's decisions. Having a system trained using only image-level labels, it is possible to provide weakly supervised lesion localization and highlight regions in the input image that are discriminant for diagnosis. How to best do this and improve current approaches is an active topic of research in AI. One example is a method developed by our group, iterative visual evidence augmentation. I hope this lecture has given you an idea of the importance and current solutions for explainable AI in medical imaging, a key aspect to increase expert trust and facilitate the integration of deep learning systems in clinical settings.